Hey folks, today we're going to be looking at something that is really common in any science field, and particularly in physics, and that's graphing data. And we're going to be using this to analyze patterns and get a general picture of what's going on outside of just the small section of data points that we're able to collect. When graphing something, the first thing we have to decide on is what kind of a graph we're going to use. For physics, the answer is almost always going to be scatterplot. Scatterplots will be the graph of choice whenever we have numerical values for two different measurements that we're looking at. So like in the data that you're seeing here, we have numbers for time and numbers for speed. And so the only way to show both of those on the same graph to look at a relationship between those two is by creating a scatterplot. Other types of graphs that you may encounter from time to time in physics would be something like a bar graph. So if we have different categories that we want to compare, maybe we're comparing the elasticity of a bounce for different balls. So we drop a tennis ball and we drop a racquetball, and we want to compare a tennis ball to a racquetball. We might have a graph where the tennis ball bar comes up this high and the racquetball bar comes up this high. We don't have a number for the ball type that we're comparing, no meaningful number there, just that it's a tennis ball or a racquetball. Parts of a whole, you might use a pie graph. That probably won't come up in this class, though. Generally, we're going to be doing scatter plots on just about everything. So we're going to run through an example of that here with the data shown. And for this, I just made up numbers, but I was imagining a situation where maybe we're watching a car drive by some series of positions, and we measure the speed that it's traveling at. We get a bunch of people out with radar guns or something. We're measuring the speed that it's traveling at different moments in time, and we have both the time when it was recorded and the speed that it was going at that moment recorded. So with this data, the first thing that we need to do, now that we've decided that it's going to be a scatter plot, is think about what goes on the x-axis and what goes on the y-axis. X-axis is always the independent variable. That's the thing that keeps on chugging along regardless of whatever your other measurements are. So the idea here is that we think that our independent variable is going to have some effect on our dependent variable, or certainly, if not a direct effect there, we can certainly say that the dependent one doesn't affect our independent one. So once I decide we're going to start making measurements of this car going by, and I click the stopwatch, that time just keeps on ticking by. It doesn't matter how fast the car is moving. So if the car goes faster, we're not going to go faster through time. Or if it goes slower, we're not going to go slower through time. If the car moves backward, we're not going to go backward in time. Time is independent of that speed. But we do think that there's some kind of a relationship between speed and time, that we should be able to see a pattern between time and speed, such that as time goes by, speed increases or speed decreases or stays constant. That's the way we're looking at this. So we want time on the x-axis and speed on the y-axis. Now we need to decide on a scale. Looking at the numbers on these will help us figure out what kind of a scale we want to use. So let's first look at the x-axis scale. So we're looking at the time. Time's going to go on the x. Our x-axis, it looks like we're going to go, we're looking at a range from 0 to x equals 8.9 seconds is our biggest one. And then on the other side, so these numbers are going to be the y-axis numbers. We'll have y equals, well, we don't go all the way down to 0. We'll think about that later on. Looks like our smallest value is down here, 3.0 meters per second. And we go up as high as, say, 13.3 meters per second. Okay, so our scale then needs to be a scale that will allow us to get all of our data onto our graph. Now, a mistake that I see commonly when people are first getting back into it, maybe they've forgotten from their math classes, is to go ahead and number the x-axis just with each one of these values. So my first square is labeled 0, my second one is 0.7, my third one is 1.1, and that doesn't work. We need to have a consistent scale across our axes. We'll find here that the shape of our graph gives us a lot of information about the relationships between those two variables, but only if we have consistent scale on the x-axis and a consistent scale on the y-axis. They can be different scales, but it needs to be across consistent all the way across a single axis. So let's look at the x-axis first, and I have a set of axes made already. We needed to go in the x-axis from 0, let's see, I already forgot the number, 0 to 8.9 seconds. All right, so I'm going to go ahead and label the x-axis. This is time, and that'll be in seconds. And I need to go from 0 to 8.9. Now, as I'm designing my scale, I want everything to fit on the graph, but I don't want everything squished too small. I kind of want to spread it out so that it takes up most of the graph that I have here. So let's look at how much space we have. If I just go through, I can count pretty quickly how many spaces I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, now a good starting point on something like this would be to take your range. Here I have a range of 8.9 seconds, from 0 to 8.9 seconds, and divide that by the number of spaces you have. So 8.9 divided by 23 in this. Now 8.9 divided by 23 is 0.39-ish. So that number, 0.39, that's the scale I would want to use if I didn't care what my scale was and how difficult it was to use to label my axes. I would use that, and that would make my data take up all of the axis that I have drawn. Now, that is not going to be a very convenient scale for us to use, just because it's a pain to work with. In general, you want all the scales on your axis to be a 1, a 2, or a 5, and you can have some zeros in there too. So instead of a 1, you could have a 10 or a 100, or you could have a decimal and some zeros. You could have 0.1, 0.01, 0.001. 2 goes the same way. 2, 20, 200, 0.2, 0.02, 0.002, or 5. So 5, 50, 500, 0.5, 0.05, 0.005. Now I'm going to go up to the next bigger 1, 2, or 5 from that number that I got. So I got 0.39. I'm going to go up to 0.5. So I know that my data is all going to fit. It's not going to take up quite all the graph space that I have, but it will be pretty close. And using 0.5 has the advantage of making the graph easier to make and, just as importantly, easier to read. So I'm going to go ahead and label that axis. I'm going to do 0.5 for each space. And just to make this a little cleaner, my 0 there, I'm going to skip lines here. So 0.5 and 1.0, 1.5 and 2.0, 2.5, 3.0, 4.0, 5.0, 6.0, 7.0, 8.0, 9.0, and I can stop there because my biggest value was 8.9, but I could go on if I needed to. All right, now on the next one, we have a range from 3 to 13.3 meters per second. We don't go all the way down to 0. So a question we should ask then is, do we want to have our scale go all the way down to 0, or should we include a break in our graph? You can go either way on these ones. Including a break has some limitations causes some problems. Number one, if you don't have data going all the way back to 0, including a break on your axis typically is going to mean that your intercepts don't have any meaning, whereas they may have some meaning if you don't have a break there. So it will change the shape of your graph a little bit in where it hits the x or y axis. It may also tend to exaggerate very small differences. Maybe there's something where we have really a constant value in the y-axis, but just due to measurement uncertainty, we find a little bit of fluctuation in the measurements we get. If we do a break in our graph, and instead of having do a break in our graph and have a really small scale, these little differences are going to look very big. Whereas if we went from 0 all the way up to whatever value we're looking at, maybe we were getting like 11 and 11.1 and 11 and 11.1 and 11.2 and 11 and 11.1, basically a constant graph. But if we make it so our scale is 0.1, for every 10 spaces there, those differences are going to be really big. It's going to jump all over the place. Here, we're pretty close to 0 anyway. I'm going to go ahead and go from 0 to 13.3 at a minimum. And I'll do the same thing I did before. I'll just count my number of spaces and divide 13.3 by the number of spaces. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And 13.3 divided by 16 gets me 0.83. Again, I'll round up to the nearest 1, 2, or 5. So that'll get me up to 1. So this is the speed. And that was in meters per second. And I'll use a scale of 1. Again, I'm going to skip lines here to keep this looking a little cleaner. 2, 4, 6, 8, 10, 12, and 14. All right, at this point, I'm going to go ahead and start plotting my points. And so on this one, I started out time of 0, 12.1 meters per second for my speed. So 0 for the x-axis and 12.1 meters per second for the speed. And I'll continue going through each data point like that. And now that those are all plotted, we can see our general shape here. What initially looked to me like an increase and then a decrease in speed now may actually, depending on how uncertain our measurements were, that may show a consistent decrease in speed just with a bad data point collected toward the very beginning there. So we don't really know, it was made up numbers. We don't really know what the uncertainty in the measurements was like. But maybe this is actually showing a car that's slowing down the whole time at a fairly consistent rate. Certainly, most of this graph seems to show that. We may have a little bit of an increase at the very beginning, maybe a little bit of an increase there too. And that's consistent with driving a car. You don't really go at a constant speed the whole time. You slow down and you speed up a little bit as you go. But on this one, if I were looking for a general trend, I'd say that looks pretty linear. Now, when I make that determination, I also probably am going to add to this graph a line that represents what I think perfect data would represent. Perfect data probably is not going to look like you're playing a game of connect the dots. If we expect that something shows a general trend, and we're trying to express that general trend, we should show a line that, or a line or a curve that also has a general trend to it. So for this one, let's say that we expect the car was doing something consistently the whole time. Maybe in this case we think the car was coasting and slowing down the whole time with a little bit of measurement uncertainty in there. And if we had been able to measure everything perfectly, we think probably there would have been just a straight line, a linear relationship between time and speed. So if I add something like that, I want to be precise in what I'm doing. I'm going to go ahead and use a straight edge for this, which is a little bit tricky on a tablet type platform, but I think we can make that work. Alright, use a straight edge and plot that straight line all the way down. There we go. Hey, not bad. Alright. Now what I don't want to see on data, what we shouldn't have here, is just total chaotic, like I said, connect the dots types of patterns here, or lack of patterns, because that's saying we think that the data we collect is perfect, and that this is just a really odd relationship where sometimes when this variable increases, this one decreases, and sometimes when this decreases, this one increases, but sometimes it flips around, and there's really no pattern to it. There are events where that happens, but typically we'll be investigating things where there are consistent relationships between the two variables we're examining. So the car driving, we could have some kind of chaos there, but here we see it looks like basically a consistent pattern. We'll get plenty of practices with this over the course of the year. Please do let me know if you have questions, either in person or by commenting on this video. If you learned something, also please be sure to like or share this video with somebody you think might get something out of this. Thanks very much for watching.